Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very, very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, PiPION Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. PiPION Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you are watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on a YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream.
You got that timing down so well.
I wasn't going to say anything. It was smooth. I thought I was late. It was like 1 second left.
I don't know.
Or something. It was so good though.
It was very good. It was a great transition.
Look, I'm a pro at this point, it comes with practice, time, dedication. It's the 10,000 hours rule. If you spend 10,000 hours doing something, you become an expert.
That's right.
That's the theory or whatever. But I don't know that I've spent 10,000 hours doing this, but I'm already an expert.
Well, you've spent at least over. This is now the 97th episode.
That's right. But we haven't done this exact video for all of them. This video intro switch thing has probably been like 10 episodes worth or 20. So I've spent about 20 seconds total. So I'm almost at 10,000 hours. You know what I'm curious? 10,000 hours divided by 24. It's 416 days in a row, like without sleeping. So if I just click this button for like a year, I do nothing. I don't sleep. I don't eat. And all I do is click a button to go between the video and us live. I'm telling you. Yes, it's gonna be even better. Well, that was amazing. Yes. Welcome everybody. Thank you for joining us.
All right. So we got some questions to start off with. Sandeep Chowdhury has a question. I have extracted Mott-Schottky data from desktop 1 over, I think that's the space charge capacitance squared. And then I don't know about 1 over CP2. Maybe that's also space charge capacitance. I don't know if that's supposed to represent another thing.
And voltage. Yeah.
And voltage.
So you don't know why 1 over CP squared and 1 over CS squared values are 0. Well, first of all, I mean, my ability to answer this question is going to be severely limited. I don't have access to your data. I can't.
Yeah.
I mean, I don't know how thoroughly I'm able to answer this, but generally speaking, you probably just made a calculation error. Like, I don't know what else it would be here. Mott-Schottky involves taking impedance at a lot of different voltages. And then the key is, how did you take the impedance at each voltage? What was the procedure? Did you take one data point, one frequency, or did you take a full range? And then did you do a circuit fit, or did you do did you just let the software tell you what the capacitance was, or did you calculate it yourself? There's a lot of follow-up questions that would be required for me to, I guess, adequately know. And then, conventionally you'd say if 1 over something is 0, well, the thing is very large because 1 over a large number, and it's usually, it's usually the exact opposite. The capacitance is usually like, let's just say a microfarad or whatever, like some number in that range. And then you square it. So it's like 10 to the minus, so like 1 times 10 to the minus 6 squared is 1 times 10 to the minus 12. And it's 1 over that. So it's like 10 to the 12, right? Like 1 over C squared dimensionally is usually like a large number. So like the y-axis on a Mott-Schottky plot is large. It's large numbers. It doesn't matter. Like, you're looking for the fit, you're looking for the space charge capacitance or the electron donor density as part of the slope or the intercept. I'm just saying, mechanistically, if you're getting 0 when you should have like 10 quadrillion, you've probably just made some calculation error. I guess.
Yeah, literally, if it was switched, if there wasn't a minus sign on the capacitance, like, if it did, instead of it being 10 to the minus 6, it was 10 to the 6 and it was in the denominator, and then that got squared. Oh, then 1 over 10 to the 12 is 0 or something.
So he's trying to clarify, but I'm still not sure exactly. He says, I extracted the data to plot Mott-Schottky, but I don't know 1 over c squared extracted data are 0. I don't know those data are why they're 0 or that they are 0. But in graph, those values are not 0.
Yeah, this seems. I mean,
understand what you're. What I guess I don't understand. I think that might just be. Yeah, in graph they're not 0, but
yeah, but you're
what
just
are you
like
saying? Are you saying
you exported the data from the graph, and in the graph export it's 0. So that sounds almost like it feels like a computer issue, because you can see visually that the data points are not equal to 0.
In graph, those are. I think I'm not sure of your question, and I think honestly, this is something I would need to see data to know what is going on. Again, it's the way that you calculate the capacitance and then you invert it and square it is just a mathematical. The way you calculate the capacitance is often a mathematical thing, but sometimes it's a circuit fit. So it matters how you're extracting C and whether you're extracting the correct C. If you're, it sounded like a beginning question. You had two capacitances. So which one is which? There's some open questions here. I think we're going to have to move on, because I guess I don't 100% know what you're saying. You're saying that in the graph, those are not 0. Okay. And so apologies if there's just a bit of a language misunderstanding on my part here. I don't understand. You're saying your first question said the values are 0, why? And you say they're not 0. And I don't understand precisely what your question is. So
all right. So he's saying, I'm asking why exported data does not showing any values, but in the graph I am getting proper 1 over c squared versus potential graph.
Oh well, this is just a which software are you using? I don't know, right? I mean, this sounds like a mechanism, like a software problem.
Yeah, it sounds like an exporting issue in your software. And that when it goes, like when you do have like a very small value, does Excel round it to something like
or
0,
a big value,
or if it's a really big value,
is it overflowing? I don't know. There's something. This sounds like
a software.
This
problem.
doesn't sound. Yeah, this doesn't sound like a science problem. Which might be a good thing. It doesn't sound maybe like your experiment is poor. But there's just a problem when you're trying to extract the data. And so I don't know what software program you're using. Obviously, if it's our software program, I can try to help with that. I'm just sort of I'm pulling up. I don't know if I have a
sample.
Just as an example. So here's one example, just for the sake of clarifying Mott-Schottky, I guess. Here, where's our software? So here it is. This is some Mott-Schottky data. It looks like I did this on titanium dioxide last March. For what it's worth, I don't know. I was playing around with some stuff. So anyway, you can just see I have 1 over c squared, and it's, like I said, it's like 10 to the, I don't even know, whatever that is, like 10 to the 7 and whatever. And then voltage is on the x-axis here. And I'm guessing if I extract this, I'm not going to get zeros. I'm just going to, I know you can't see this. Let me stop sharing. So if I'll share my screen. It's going to be trippy for a second. Okay.
Yeah.
So if I copy this data and I come to Excel and I paste it, you see X values are the voltage and is point whatever. And then the Y values is the 1 over c squared. And these are the same values that were on the plot. So, every software is a little different. This is the Mott-Schottky plot. This is the same thing as you're looking at just in Excel versus in our software. So I don't know. There's some software issue you're dealing with, I suppose, is probably the result. I don't have much more to tell you than that. I mean, just make sure with the manufacturer or whatever that things are being copied to the clipboard, right, or whatever the mechanism is there. But hopefully something that's quick-ish to solve, right? If it's just if it's just kind of a software thing. I hope that's not a science. It sounds like it's not a science thing, which again is the good thing. It means you're probably not doing anything wrong scientifically. Just a bit of a copy paste thing. So
okay, let's go up. Got
do you want to answer the saved one, which was the first thing there? Or do you want to get to the live ones?
I guess we'll get to the live ones first. So that I mean, these questions are from Wang Kailai. I think that pronounced that right, Kailai. So we got a bunch of questions from him. We'll try to get to them somewhat in the order that they were asked, but there are a few people ahead of you for some of the questions. But we can get to some of them now, and we'll get to your saved question later. But basically, your first question, I think, is very simple. Can you explain what is the definition of overpotential? So overpotential, in very simple layman's terms, is just the potential beyond the E naught or the thermodynamic potential to drive a reaction forward. It's most commonly shown in the Butler-Volmer equation. So actually, if I click this and then Kotecky-Levitch, no, cycle retention. Tafel. So Butler-Volmer. So you'll see this E minus E0 in the beginning, or in the middle of the equation. I can't actually point to it. But the E minus E0, that is the overpotential. The difference between the E and the E0, if E0 or E naught and E are equal to each other, then you have zero overpotential. But when E is any other value than E naught, then you have an overpotential. And it can be a negative overpotential. It can be a positive overpotential. And it's just when they're not equal to each other, and you don't have a zero in the exponent of this equation, then you get current to flow in one of two directions, depending on the concentration of your oxidized and reduced species. So that is what overpotential is in kind of layman's terms, sort of say. And let me know if that makes sense. If you needed something a little bit different than what you're interested in, but that's the very simple, straightforward definition of overpotential. Okay,
just go in order, I guess.
Yeah, I guess we can go in order now.
So the next question's a battery one here by Ahmed, who says, why for batteries research we measure EIS for lithium cell and LSV for lithium aluminum cells, while the most important are lithium NCM coin cells, also which is regarded as a suitable range for measuring CV of coin cells. I don't think you're identifying these things properly. I don't know of any particular reason to believe that only impedance is used for like lithium symmetrical cells and not for anything else. I don't know that to be true. Certainly possible. There's something I'm not quite knowledgeable about, I suppose, but I don't find that necessarily to be something I would agree with. Like, well, lithium cells are impedance, and you can't do impedance on lithium NCM or lithium aluminum. There's no specific reason you can't do any electrochemical test on any of these things necessarily. So I guess I don't quite understand where you're coming up with this idea that like you can only do one thing on one or whatever. Now the as a general rule, I guess or as a general, I don't know, comment or something, I guess I'd say like when you're studying a lithium and then something else cell, it almost definitionally means you're studying a half cell. Okay, so if you're doing like a lithium NCM, that means you're studying the cathode and you're using lithium as the anode. It's not a full battery, right? A full battery would be like NCM and graphite or whatever, or LCO or LFP and graphite. So if you're studying a coin cells, and you're studying a cathode material or an anode material, and you're trying to like isolate the focus on how good does this cathode or this anode perform, you put lithium as the other side to work as the like ideal reference / anode or cathode counterpart. Okay. Now, in doing that, you do often run either LSVs or CVs, like very, very slow scan voltammetry you can do to identify, just as you would with any CV, like the peaks that show a Faradaic process, which in the case of a battery, when you're studying an anode or a cathode, is like an intercalation or a de-intercalation process. With a cathode or with an anode, sometimes you get multiple different peaks, or you get plateaus, or you get stuff like this, because it's a complicated process. Sometimes there's multiple steps involved, and it can be a little bit kind of fun to see the behavior there. So you could do LSV or CV on any of these materials. But if I'm guessing that, for example, just as an example, if you have a lithium cell, like a symmetrical battery made with lithium at both sides, it's probably because you're studying electrolyte or separators. There's really nothing to be gained about the anode or the cathode when both are just plain lithium. It's not a novel material, right? It's like you're just putting lithium both sides. So that would be a case where, for instance, you want to study the electrolyte, and so you use like ideal anodes and cathodes, and you can see how well the electrolyte holds up, or something like that, or a separator, or some of the other pieces. It's like a typical scientific experiment, I guess you'd say. Like, you're isolating the variable you want to study, the anode or the cathode or the separator or the electrolyte, right? And you try to use ideal materials for the others, so that you don't, like, if you're trying to study a novel cathode material, well, don't also use a novel anode material and a novel electrolyte and a novel separator, because which one is contributing positively or negatively? It's too many variables at once, right? You're trying to control for things. And so maybe what you're referring to in some way is like, if you have a symmetrical cell, you wouldn't run CV or LSV. Or if you have lithium aluminum, that might be because you're using it for blocking conditions. And so CV isn't really needed in this case, because it's mostly just capacitive behavior. And so you would do something like, I don't know, maybe you would just do LSV to study the capacitance, like you would do like for a supercapacitor. Or if you have blocking conditions, you would just do impedance, because you're just trying to study the like ohmic resistance or the double layer capacitance. So these are some ideas, I guess, but as a general rule, like I don't know if this is exactly what you were saying in your comment, but there isn't really like off limits kind of experiment necessarily, just because you have one kind of anode or cathode. I mean, folks do galvanostatic charge discharge and impedance and some voltammetry to a lesser degree, but still a little bit on batteries of all kinds. So I don't know that if that's exactly the point you're making, but that's kind of my summary of that.
Wang wanted a little bit more clarification, because he didn't understand what I meant by the word thermodynamic potential.
Oh,
so
boy.
I'll spend a little bit. Don't worry, there will not be any mention of
electrochemical potential.
That's correct. I will not use the phrase.
Well, I'm sorry I even brought it up.
It's okay. I understand it a lot more now. There are still aspects of electrochemical potential that I don't understand.
Nobody likes electrochemical potential.
Yeah. Except for Dan.
You're like, yeah, I guess you're right. You have no rebuttal.
well, it's like no one talks about it, and yet it is the thing that drives electrochemical reactions. But it's so weird.
But it's so universally hated. It's a little weird.
It is. Well, I'm bringing you up to my my number one favorite equation. This is the Nernst equation. So when we talk about, I was referring to this like E naught value before. So this is what I meant by the thermodynamic potential. So a little bit more about this. So in thermodynamics, we usually talk about things like delta G, right? Or delta G naught. And there's a relationship, which is delta G naught is equal to negative NF E naught. And this relationship basically is that the Gibbs free energy of the system is equal to minus, mostly just for sign conventions, the number of electrons transferred, the moles actually, times Faraday's constant times the electrode potential, the standard electrode potential. And so when we use this not here as kind of the standard potential, we're talking about things that happen at like 25 degrees C, 1 molar, 1 atmosphere. These are what we call standard conditions. And it's a constant, right? This is just a constant. And then everything around it, we can just take our constant and then we can add and subtract things around it to help us describe the system, how the system is changing. So when I say, the overpotential, which is sometimes uses the character mu for overpotential, is E, the potential minus E naught. And that's what the overpotential is. So the overpotential is a relationship, if you will, between this kind of value that's related to thermodynamics, and this is also related to thermodynamics, as you know, the regular E is related to thermodynamics as well. But as this changes, and you can even see it here in the Nernst equation, at E naught, the thermodynamic potential, the concentration or the activity of redox species, the oxidized and the reduced species in this reaction, are equal to 1, or they're equal to each other, which gives you the natural log of 1, which is 0, and the potential is equal to the standard redox potential, the E naught. And moving to an overpotential, any potential that's not E naught, you're going to induce current to flow, and you're going to change this ratio. You're going to make it either positive or negative. And that also goes back to like the Butler-Volmer equation, where when these two guys are equal to each other, both of these things go to 0. And this whole term, you get current is equal to 0. But if these are different for whatever reason, because we changed it, this value, this whole exponent multiplied by the concentration and this difference is going to drive some current to flow in your system. So overpotential, really, it's just this equation right here. It's just this expression. And it's a way of saying, oh, how much more potential beyond this thermodynamic value are we driving the reaction forward in one direction or another? Are we making more of this reduced species or more of this oxidized species? So hopefully that helps. I don't want to go into thermodynamics per se.
It's a little much.
It may be a bit much, but of course, if you ask, then we have to get into electrochemical potential, and then we're not going to be happy.
Yeah, nobody will be happy. But
no one will be happy.
But you know, you could talk. It's like a thing you could talk about forever, which is potential. It's like the fundamental unit of this discipline, and yet you could talk about it for like 45 minutes.
Yeah, that's right.
It's a lot.
It's a lot. It's a lot.
Until then, we'll move on to questions that are more digestible, like what is RCT and how does it differ than Warburg element? Well, RCT is the charge transfer resistance, and a Warburg element is the impedance related to diffusion. I don't have a lot more to say than that. That they're just different circuit elements. When you have a process that is occurring, some like related to the overpotential that Alex just talked about, it's related to a Faradaic process. The E0 is related to a process that's happening. A plus an electron goes to B, right? There is some ease or difficulty with which that electron can be transferred. RCT is a measure of that difficulty. So if the electron just goes like that, super easy, barely an inconvenience, and there's no issues, credit to Ryan George for streaming. I love that. I love that guy. I couldn't help myself. That was good. It was a good use of that phrase.
That was a great use of the phrase.
I love pitch meetings for anybody who watches those. Anyway, if the electron moves super fast, it's not difficult at all. There's nothing in the way. Then it has a low resistance, a low charge transfer resistance. If it's if it's hard to do, it probably means the kinetics are slow and there's impediments for one reason or another. The RCT is fast. That's just what it is. It's a measure of how easily the electron moves, basically. And the Warburg is, again, quite simply the impedance related to diffusion. Diffusion is the movement, random movement of ions, basically reagents. If some species is floating around randomly in solution, and it's the A that can react with an electron to B. Well, it has to move its way randomly. Over time, it'll happen to move right close to the electrode surface, and then poof, it can turn into B. And so Warburg is the measure of that diffusion, basically. And so that manifests itself on an impedance plot as well.
Yeah, I have a whole video on understanding Warburg impedance on the YouTube channel. I'd recommend you take a look at that for more clarification on Warburg impedance.
So I did a webinar Tuesday for the University of Southern California. So if anybody here is from USC, thank you for that. I'm not sure, I doubt it, but anyway. And somebody asked a question about why the Warburg is 45 degrees. And so anyway, I was like, my colleague just gave a video about that, actually, you know, and I briefly talked about the y-axis is time and the x-axis is distance.
It's a way of thinking about
it. It's a really, but I like that. It's a really good way, because they're at a 45-degree angle, the diffusion is happening at a rate, like according to a rate, like a diffusion coefficient, right? It's how many centimeters square per second it's moving. So it's like time is going by and things are moving at a set speed. And so if it's like perfectly vertical, you can imagine the rate limiting factor there is time is infinity, because they're a capacitor, the stuff on one side of it does not reach the surface. It's like stuck. So it's like taking infinity time to get there. Right, but the distance is set, so something like that.
Yeah.
So it's like it's a difference or an invariance between the time and the distance of molecules moving, basically, something like that.
Yeah.
So it's cool. It's a cool explanation.
It's a way, good way of thinking about it.
Yeah. Because they asked why what happened? Why do I get like a greater than 45-degree line? What does that mean? Something between capacitance and diffusion, but you can look at it as a time and a distance.
You can think about it as
it's taking longer to move a certain distance.
Yes. Yeah. So Wang has some extra questions. I think we can get through these, and then
sure.
Move on. We'll try to continue answering questions.
Yes.
Of course, ask for more clarification is needed, but we will get through questions as they come up. So what is the difference between 3 and 4 electrode systems? So a 3 electrode system, generally speaking, involves a working electrode, a counter, and a reference electrode. The working electrode is the electrode of interest. That is what you are studying. And you measure the potential between the working and the reference electrode. The reference electrode represents having a stable reference point. Current is allowed to flow between the counter and the working electrode. That's how we get redox reactions to occur. So that's 3 electrode system. In a 4 electrode system, you are able to, let me see if I think about it. I think in a 4 electrode system, you're able to kind of decouple the measuring and the driving of forces to the working electrode. Basically, you can drive current. This is what's known as like a 4-point probe technique, but the current passes through the counter and like the working drive, what we can say, and then we can measure the potential between a working sense and a reference electrode. So that's a way that you can kind of distribute it. So in the 3 electrode system, we've effectively tied the working electrode to being both the driving, the spot where potential is measured and current is driven to. In the 4.1, we deconvolute that, and we can separate out where the potential is being measured at, but where the current is being driven. And if you want to even extend it further, in a 2 electrode system, we make it so that there's only 2 points where both the current and the potential are being measured at the same point. So that's kind of 2, 3, and 4, if you would say, electrode systems.
And then it looks like his last question is pretty simple
For
explanation, actually. Yeah, for now.
For now.
Is why run impedance with a potential that's not OCP? It sounds like the question is, will it cause decrease in the charge transfer resistance? It can, but generally the purpose of doing impedance is the same purpose for doing any electrochemical experiment. You're trying to study something. What are you trying to study? Are you trying to study a reaction? I bet you are, because that's what electrochemistry is. Does that reaction occur at some potential? Cool. Is that potential open circuit? No. Then you should probably use the potential at which the thing that is happening is happening.
This is like your trigger thing. Like, why do people do EIS?
I have a hard time with this question because it's like, I think people overthink this. I think there's two reasons. One is that impedance is weird and kind of hard, and so people have a tough time. That I understand.
Yeah,
believe me, I spend a lot of my time lecturing and giving webinars on impedance because I'm very passionate about trying to educate on the subject. I really like impedance. It's part of my thing. But I think honestly, it's one of these things where when you run impedance on any potentiostat, whether it's my company's potentiostat or anybody else's, you like open the impedance experiment and the default in the software is like 0 volts versus OCP. It just every company does this. It's just, there's nothing, it's not incorrect. It's just when you open an experiment, you're going to run CV or square wave voltammetry or double amperometry, triple quad step Cottrell equation. That's not a thing. Whatever you do when you open up an experiment, there have to be like default parameters, or they're all blank and you have to fill them in, right? And so it's just natural for a default parameter to be 0 versus OCP. And I think a lot of people take that as a like suggestion, like that's what it has to be. It bothers me because it just feels like a lack of critical thinking. It's like, this is just a default parameter in the software. What are you trying to study? Are you trying to study the oxygen evolution reaction? Because that doesn't happen at 200 millivolts. It happens at like 1.2. So if you're trying to study oxygen evolution and you're just doing impedance at 0.2, you're not studying oxygen evolution. Would you do CV at 0.2, like plus or minus 10 millivolts? And just do that and be like, why am I not evolving oxygen? No, you would sweep up to 1.2 or 1.4 or whatever, so that you get an increase in your current. You're studying oxygen. Like everybody knows this intuitively. When you're doing CV, you got to set the limits to like find the thing you're looking for, or chronoamperometry, or what, you're going to apply a potential to generate your product, and you're going to pick a potential that's like generating a lot of product, and then you're going to throw it through a GCMS and see what you mean. Like these are all things that the average electrochemist would think to do, but for some reason, when impedance is involved, all of that turns off in their brain, and it's like, it's at OCP. Why am I not getting an answer? It's like, because you're not putting a potential of a thing you want to study. So the charge transfer resistance, as I said before, is the difficulty of an electron moving, right? Well, if you increase the overpotential, if you drive the reaction more, based on what Alex just talked about with overpotential, if you're more, pushing the difference between the E0, then it will be easier to do. Hence, the charge transfer resistance will likely decrease. So yeah, that's like one of the main things you're doing with impedance, and you're studying some reaction of interest, is you're studying what is the charge transfer resistance at a certain overpotential, because you're driving the reaction more favorably. And so the charge transfer resistance will decrease. The kinetics are better, faster, whatever, right? Those are all kinds of normal, I guess you'd say, mechanisms that, things that you study with impedance, one of the main, purposes of impedance. So.
All right. The next question is from Isaac Frazier. Isaac is asking, for EIS, what timing accuracies between ADC measurements are required for good output data? I have aims of about 10 to the 1, so I guess that's just 10 nanoseconds at 200 kilohertz FS, but don't know much about sorts of accuracy achieved in real systems. Right. So this is okay. So he's talking about analog to digital converters. and the timing for an EIS experiment.
Timing accuracies.
So actually, I was looking at this question, and like 200 kilohertz is about a cycle every 5 microseconds. 5 microseconds. And generally, I think the Nyquist thing is like you need to make a measurement at one frequency, you need like
one order of magnitude,
like 10 times
of sampling,
Yeah. So you would need like 0.5 microseconds.
So it's 500 nanoseconds.
Yeah, 500 nanoseconds would be the minimum speed you need to be sampling to accurately measure signal that's coming in at 200 kilohertz.
Yeah, I believe that's correct. And so if you're able to accomplish, I guess, 10 nanoseconds, you should be more than have more than enough room, let's just say, for a 200 kilohertz signal in theory. Right? 10 nanoseconds is also quite fast.
Yeah.
But 10 nanoseconds would be, in theory, adequate for a 10 megahertz signal, I believe. Because 10 megahertz would be 0.1 nanoseconds. Right? Did I do that math right? 0.1 nanoseconds is 100. So then 10 times that is 10 nanoseconds, like 10 times faster.
Yeah.
So 10 nanoseconds, the other way to look at this, I suppose, based on that logic that you just described, you could say in theory, if you have 10 nanosecond resolution or accuracy, whatever the right terminology is here.
Sampling interval.
Yeah, sure. Interval right.
Too short.
Interval too short.
That's another inside joke.
Yeah, seriously. You could, in theory, measure up to about 10 megahertz of a signal, which is really fast, right? So that is roughly speaking. Now, there's things like undersampling that you can do for fast frequencies. So you don't always need that, but I can't speak more in depth about it. It's a thing you can look up undersampling. It's a technique that allows you basically stitch together a sine wave by undersampling. But anyway, I don't want to go on about it because I don't know the concept well enough from an electrical engineering perspective, but it is a thing. And so that would be the exception for you don't need to sample at 10 nanoseconds to get, or even you don't even need to sample at, let's just say a microsecond. You can still get faster frequencies because you can do an undersampling thing. And it's definitely a possibility, but I won't speak more to it than that, I suppose, is what I'll leave it there.
The only other thing I would mention, and I need to pull this up, is the accuracy contour plot, because you're talking about accuracy.
Right.
So even if you're able to achieve, where is the accuracy?
2.3.2, something like that. Keep going down. It's right after the specs.
There we go. Thank you.
Yep.
So let me just share this with you quickly. So there's the timing which is very important, but also even if you can go very, very fast, there is an accuracy to your impedance that's described by the quote accuracy contour plot. And so as you can see, yes, we can, this is just a sample for our wave driver 200. I think it's the same as the wave driver 100.
Yes, it is.
And there are certain impedance limits in the on the y-axis to how low as well as how high you can accurately measure the impedance at a particular frequency. And as you can see, as you go to higher, this is general, this is just an example of ours, but almost every potentiostat where you look up the accuracy contour plot, depending on how, what your system is, the accuracy of your measurements will depend on what the impedance of that measurement is. So we're very accurate at 1 megahertz. We're very accurate within, this band. But then as we start to go outside of this band, the accuracy changes. It goes from 1% and 1 degree, because there's also the phase. The phase angle is another thing of accuracy that you need to be aware of when making your EIS measurements. And then after a certain point, it's like, well, then you have 5%, right? 5% and 5 degree accuracy. But then at a certain point, if you're measuring very low, things with very low impedances or very high impedances, your accuracy will decrease. So when it comes to the accuracy of the measurement, besides just the time resolution and sampling, there's also there's another limitation in terms of accuracy, which is based on this accuracy contour plot. So that's just another thing to keep in mind as you're doing your experiment, basically.
Yeah. It looks like the last of Wang's question here was, I don't know, I vaguely remember this. Maybe you talked about it. I can't remember. But 2 weeks ago, talked about the self-assembled monolayer will cause the increase of solution resistance, but not sure if it'll increase solution resistance or charge transfer resistance. I suspect, I guess I don't understand why it would increase the solution resistance to begin with. I guess we talked about that before. It would it could increase the like overall uncompensated resistance. I mean, if there's an electrode and you have a monolayer on top of it, it won't affect the electrolyte itself necessarily, but it would increase the ohmic uncompensated RS, like leading resistor, just because there's another barrier. And so it's like the intrinsic resistance associated with the electrolyte plus the resistance of some monolayer. If that's what you mean by like increase the solution resistance, I think that, because it's just like you've drawn before, it's a sum of two resistors. So it would aggregate to make it bigger. But will it increase the charge transfer resistance? I mean, if it participates in the kinetics, I suppose. I don't know. I don't know much about self-assembled monolayers, to be honest, or the context of whatever the specific reaction you're studying is. All I would say is it's possible, I suppose, right? If the monolayer is part of the catalyst or is the catalyst, or I don't know. Like, I don't know precisely what it is.
I'm gonna
maybe not.
I'm gonna go off on a limb, and I'm just gonna say it probably wouldn't. That's my guess. Like, charge transfer resistance has to do with kinetics, and usually, I mean, there is when you talk about heterogeneous electron transfer, yes, if it was heterogeneous electron transfer and the nature of the and the nature of the metal itself played a role, then it would. But we're talking about a self-assembled monolayer. You've blocked sites on, say, your gold. You have a gold thiol self-assembled monolayer. You can still have electron transfer to species. It's just like, where does the field, there's always a tunneling mechanism, which means that.
So that's homogeneous.
So this would be homogeneous electron transfer.
Yeah.
And homogeneous electron transfer rate kinetics are based on the molecule itself.
Yeah, so that shouldn't be impacted by the monolayer. Now you might have worse current, for example, because of the resistance from the charge, like the monolayer, but the kinetics, if you could isolate the kinetic contribution from the other stuff, the kinetics would in theory be unchanged, is what you're saying. I think that's probably correct.
Yeah. And the
if the reaction is taking place on the underlying thing still, and that's right.
Yeah. And then you get into other weird questions, like if your self-assembled monolayer is functionalized with like electron withdrawing groups or electron donating groups, does that affect your metal center when it's then it becomes a heterogeneous electron transfer problem.
And then it is affecting
the kinetics.
I think that's why I was hedging my bets with my answer too, because I was like, that's the stuff I was thinking about. Like, does the monolayer impact the metal sites or in any way? Then it would. But if it's just a layer that's kind of physically in the way and you still have tunneling homogeneous electron transfer, then no, in theory it wouldn't. It isn't going to affect it at all. You just have like a gold surface that is doing its reaction. And now it's got junk in the way, but it's still doing its reaction. Well, the kinetics are unchanged. It's just you have junk in the way.
Yeah.
So maybe it's something like that. So
but I've been reading about aptamer-based electrochemical biosensors. And so there's like a 6-chain carbon thiol with a linker with an aptamer, and then you have the redox species. And when the redox species moves closer to the edge of the monolayer, it undergoes an electron transfer. There's all these like nice square wave altimeters. So, and it all happens at the same potential the whole time. So it's not like it's shifting around or they're getting less current because necessarily their monolayer is changing. So that's why I'm thinking like, probably it might not have as much to do, but it affects a couple things. It definitely affects a few things.
All right. RR has a question. How to get a proper EIS spectra for a stack, a multi-cell, as it's not coming properly means not a proper semicircle. So first of all, if you're trying to get impedance on a stack, you are necessarily getting some sort of combined aggregate response from every single cell in the stack. So so this is a really tricky thing, right? It could be a number of things. It depends if you're how much in series, how much in parallel your stack is. One of the mistakes that people can make, I suppose, when trying to get impedance of a stack is that your amplitude is not high enough. Maybe the signal's poor. If you have, for instance, try to think about this on the fly. If you have a lot of cells in parallel, for instance, the voltage is the same, but the current is additive, right? So let's say you have like, I don't know, 10 cells in parallel, 1s10p or something like that. Sometimes you try to get impedance across the whole thing. So one is you're going to get an aggregate impedance of everything. So that can mess with stuff. For instance, if you have, if you've, usually this happens sort of by accident, but like the cells aren't all at the same state. Like they would ideally all be at the same state and just adding. So you get 10x the delivered current or delivered voltage or power or whatever. But if the cells are in different states and it's not behaving properly, then you can get some weird stuff happening there. So that could be it. But also like, again, if you have like 10 in parallel, you're going to need like probably 10 times the amplitude. So if you would normally do like a, 10 milliamp galvanostatic or 10 millivolt signal, you're going to have to increase that because there's a lot more current, because it's like the signal to noise ratio will be poor. So that might be, something that's a problem there. But otherwise it's also, you impedance on a multi-cell, and I'm sort of assuming here, it's like you're going to have two terminals. You have an anode and a cathode, but it's like you have the ends of the whole thing, and within there's multiple cells. It's like the signal's going through every single cell. So if it might mean that you have like one, like if the impedance of like one or more cells that are in you have one cell or something, or some set of your cells that would exhibit a semicircle, like should it exhibit a semicircle, but the other cells are in a condition like they're overcharged, they're over discharged, I don't know, something of that nature, they're not going to just exhibit a semicircle. You're going to kind of have some convoluted signal. It might be why you're not seeing the signal you expect to see. It's like all the cells are not at the appropriate voltage or charge state, or something could be asymmetrical, you would say, but between one or more of the cells, and it's convoluting your EIS results. That could be what's happening as well. And there's a lot of times like battery management systems and things like that, they have diagnostics for this, like when the impedance result doesn't look a certain way, it indicates that there's asymmetry among your cells. That's where you can get dangerous, because then you could overcharge or over discharge, for instance, when you proceed as normal, without taking into account that one cell is already too high or too low compared to the rest of them. So those are just some of the thoughts I have about that. I mean, of course, as a general rule, I can't speak perfectly well to it if I don't see the data, as with a lot of these things, but hopefully that's some, I don't know, general advice for taking impedance on those kinds of systems. Okay, Sandeep, we kind of went through already.
Through that.
So Abderrahman is next, I think.
Yes.
Okay, so it says, hello, I'm working on solid polymer electrolyte. Okay, and conducted an EIS measurement. However, I still don't know if there's a difference between a test down and a test up. So like from 80 to 30 or 30 to 80.
And he continues.
Does it depend on the type of polymer I'm working on? That's a great question. Well, I mean, the most direct answer is to do the test and see if you see a difference, right? You know, let's just say in theory. Well, okay, let me back up. Yes, absolutely. If the obvious thing here that I can say is that if your polymer has a like glass transition temperature or melting temperature or something happens to it at 70 or 80 C, then yeah, obviously you're going to um, you could transform your material at the high temperatures, um, you know, and so it would certainly make a difference with your results. Now, if the polymer, in theory, has a wide thermal stability, like temperature range, let's say the polymer doesn't begin to melt or even do anything interesting, whatever, until like 200 C. I would expect there would not be a difference. And the ideal situation would be to do, for instance, I did something similar. Let me just give you an example. I did impedance diagnostic tests when I was a postdoc. Okay, on some batteries. Okay, but it was a similar kind of a thing. It wasn't solid polymer per se, but it was, you do batteries, and I would do impedance at a variety of temperatures. And so what I did was I would go like 30, 40, 50, 60, 70, 80. Okay, fine. And I'd take impedance at each of those. And then I go similar to you, 80, 70, 60 for whatever. And then I'd go 50, 80, 20, 70, 40, 30. I'd jump around. And I'd try to make sure that whether I went from down to up to down, or all over the place randomly, that the data at each temperature was the same. And you know, or within reason, and then you can average it or something like that, right? But the point is, if that doesn't happen, then it's telling you something, obviously. One of them could be that the construction of your materials is poor, or you've made an error, and it's a time thing, like time spent testing is causing the material to decompose or delaminate or something of that nature. That's not good. Or, if you see a distinct difference between the temperature differences, then the temperature is affecting. You've reached a limit where the temperature is impacting, irreversibly impacting your materials, right? But ideally, it should not depend on it if all the materials, not just the polymer, but all the materials are thermally stable up to 80 degrees C. It shouldn't, that again, that's what you would hope to see. I mean, like, experimentally, maybe you don't see that. But what I would hope you would see is that no matter which order you do things, you see roughly the same data at at those temperatures, regardless of where you started. And that would be a good sign to prove the stability of your materials at these temperatures, if that makes sense.
Yeah, I think that's good. It does sound like a engineering
it's absolutely an engineering thing. It's like mixing up the order and making sure it still works and all that. Yeah, for sure.
Yeah. So M13N asking a question. I am new with electrochemical techniques like CV, LSV, DPV, square wave, etc. I am planning to work on biosensors. So any suggestion on what reference should I go for? What are the differences between the between above mentioned?
The techniques, I guess, or the references?
I guess the techniques. What reference? I think you're just referring to like a book. Like, what book should you read, or what?
What reference electrode, or what?
I guess he just says what reference. I guess I thought he was talking about information on learning stuff, but
that's probably what he means. I don't know. What my mind went to reference electrode.
Maybe reference electrode.
You're probably right, though. I think I must be wrong.
No, I'm not. I don't know. Well, you know what?
Because he didn't say what the system is, just as biosensors.
Yeah, just biosensors.
I'm not sure why I was stuck on reference electrode, but I think you're probably right. This sounds like an education question.
We can answer both. Sure. We can kind of give like. So in terms of a reference like book, there's always Barton Faulkner, Electrochemical Methods, the 3rd edition. Electrochemical Engineering is another book. I've heard about a bunch of echem books recently, but I don't really know all of them. Barden Faulkner, the 3rd edition, is the latest one. 2nd edition might be out there that's a bit cheaper or less expensive, but covers most of the same information. That's just for learning about electrochemistry. There is another book, Kissinger and Heinemann. Laboratory technique. It's called Laboratory Techniques in Electroanalytical Chemistry. And so that book it's this yellow book, 2nd edition. So Pete Kissinger and Bill Heinemann. And that has more to do with electroanalytical techniques. So that may be more helpful when it comes to learning about some of the actual techniques themselves. So let's see. So what are the differences between the techniques above? So cyclic voltammetry and linear sweep voltammetry, I always think of these as almost the same thing. A cyclic voltammogram is a combination of linear sweep voltammograms. Linear sweep voltammograms are just when you take the potential and you sweep it. You go from one point to another point, and you just you sweep the potential linearly over time as you go from one potential to the next, or it can even be down. And in cyclic voltammetry, we're just doing that multiple times. We're going from one potential to another just over time. So linear sweep voltammetry is really useful in combination with like a rotating disc electrode, where you only need to go one direction. But sometimes cycling and going back tells you a little bit more information about the kinetics, the thermodynamics of your system. Differential pulse voltammetry, DPV, is more of a detection limit technique. It is a pulse sequence that's designed to remove background Faradaic and non-Faradaic current so that the analyte that you're trying to detect and look at is more clearly visible. So it's used a lot if you're trying to detect, say, micro or sub-micromolar concentrations of species, where you may have very large background signal just because of the nature of your working electrode. Well, you can minimize, or there may even be a background Faradaic process with the synthesis or formulation of your biosensor. You can remove some of that background signal with differential pulse voltammetry. And then the last technique, square wave, is actually the technique that most people who I see work on biosensors use. So square wave voltammetry kind of blends cyclic voltammetry and differential pulse voltammetry. So it is a pulse technique like differential pulse, where it's kind of spiking the potential, going up, and then it's moving. But in square wave, you're kind of going back and forth at an even pulse distribution. And that even pulse distribution becomes an effective scan rate, if you will. So square wave has kind of the advantage of removing background current, just like in differential pulse, but it can move at the speed of a fast scan that you get in cyclic voltammetry. So most people who are working in biosensors, at least from the very limited small amount of stuff I've read, tend to use square wave as a technique for biosensors, primarily because you can detect very small analyte concentrations, very, very small analyte concentrations, which is usually what you're looking for with a biosensor. And it's fairly accurate. Like, it's better for quantitative information. CV has a little bit more variability in the data that it can generate. Like, it's hard to get very consistent CVs for say doing biosensor work. It's not bad to do CV of a biosensor, but square wave is much more, it's used a lot more. So actually that's the technique I tried to learn a little bit more about. There's slightly different mathematics between square wave and like CV in terms of understanding what the current values are related to, but square wave is a very powerful technique. And And hopefully that kind of helps you learn a little bit about the difference between the different techniques, kind of in a short summary. But if you do want further clarification of what these techniques are and how they work, just let us know and we can talk about it. All right. All right. So moving on, let's see. We have Ali Jazz. Good to see you. Thanks. Have a quick doubt. How can we calibrate the reference electrodes? Silver chloride. I think it's chloride ion. Yeah, I think it was the chloride ion. Calomel or mercury oxide OH minus. Oh, I see. You're saying the silver chloride with the chloride ion, the calomel, mercury oxide, and then mercury oxide is OH minus. How do we calibrate these reference electrodes if we can't have a standard hydrogen electrode with us? This is a very good question. So there's several things that you can do. If you by chance happen to have a silver chloride and a calomel electrode, or you have multiple electrodes, you can do an open circuit potential experiment. So let me just, I'll just draw. Let me just make sure that I'm sharing. Yeah, so let me go to the bottom here. So let me just draw this for a minute. So if you have a cell, some kind of some cell, it's got some solution in it, some electrolyte, you can put two electrodes in here. So this, let's say this is silver chloride. All right, so this is AgCl. Cl. That's one reference electrode. And then let's say you have another, and this one, I think mercury kind of looks a little bit more like this. So this would be your calomel electrode. So calomel. And what you can do is you can measure the open circuit potential. Use like a voltmeter and kind of connect these two guys together. So you'd look at the OCP of this. And the OCP will measure the potential difference between these two. And what you want to do is you want to compare the OCP value that you get for those two pairs with that of the literature. And so let me show you one thing. I'm just going to share again, share my screen. So this is the PiPEION Research website, which you should go to. We have a tool called reference electrode conversion. And under reference electrode conversion, this is very helpful when you're just kind of comparing the difference between different redox couples and things like that. But basically, what you want to do is you want to take whatever your OCP value is, and you want to compare it between what these different redox couples are. So we can just read it right here. So calomel, let's see. So this is right. So calomel is here. Its E0 is 268 millivolts. And silver chloride is 222 millivolts. And so you would just look at the difference between these two. And I'm just going to use a calculator very quickly. 268 minus 222. You should get a 46 millivolt difference when you do this open circuit potential experiment, approximately. If you're off, if you're getting something like 35 or 30, you're like 15 millivolts off. One thing that you want to make sure of is you want to double check the chloride ion concentration in both of these. They should ideally be the same chloride ion concentration. They should be saturated. That should be the easiest way to do it. As you can see, you can have many different chloride ion concentrations for calomel. You can also have many different chloride ion concentrations for silver chloride. So as long as those things are the same, you'll be able to look at and tell what the difference is. But that's the way, if you don't have a standard hydrogen electrode, because this is difficult to create, take two where you know what the literature value is supposed to be, and then compare them. And then once you know that you have a good one, you can then just take two of the same, like two silver chloride reference electrodes, because you're working in an aqueous chloride environment. And as long as the potential difference, you can do that same OCP experiment. Well, the open circuit potential difference between silver chloride and silver chloride is 0. So you should get like 0 or 1, or you can go up to maybe 5 millivolt difference within error. But that is a way of determining whether or not your reference electrodes are good. And in terms of calibrating, in terms of trying to calibrate these guys, the only thing that you can really do is you can refresh the solution. So you can clean out the frit of your reference electrode to make sure that that's not blocked. And then you can put in new, say, silver chloride or potassium chloride solution into your electrode. Let it equilibrate over time, give it like a day or two, and then perform that same open circuit potential experiment to see if the potentials match up. So that's like the way that you would go about checking and even calibrating your reference electrode, is to use other reference electrodes with known literature values and then compare it to the literature value. So hopefully that was helpful. Hopefully that helps answer your questions and any doubts that you may have.
So Sidhu has this question, and I had to just look at a little bit into just a little bit of some literature. Just I don't have a perfect answer for you, but please suggest a stable redox mediator having a negative redox potential for my bioanode to achieve a high OCV when scaled up to a fuel cell. So I don't have a lot of personal experience with mediated electron transfer or mediators. It looks like people tend to use things like quinones and various. There's a lot of like quinones, like this one paper was talking about. Hang on, I'm going to read it. It's a great name. 910 anthraquinone 2,6-disulfate, AQDS. So there's a lot of that kind of thing that goes on along with polypyrrole. But from what I can tell, the tricky part about these mediators is that you have to keep replenishing them, because with the microbial kinds of fuel cells or whatever. I understand what you're trying to do. You're trying to create its potential. Like it's not intrinsic to the material. That's why you have a mediated material. And so the mediator, whatever species, has an associated potential with it. And the more negative that is, creates a higher voltage for your fuel cell naturally, because it's cathode minus anode. So a more negative mediator. The problem is, as you find materials that have more and more negative whatever, you're probably going to have to replenish them more frequently. They're going to get used up. And that's tricky. So to a certain extent, I don't have a specific answer to you. It's probably something like this. Some of these quinones or azenes, or there's a lot of complexes. I cannot simply tell you which one. I don't know enough to give you some answer like, well, this is the material you should definitely use. You're going to have to, I don't know, look in the literature or just try a bunch of different things you can get your hands on, that have reported negative, voltage, standard potentials associated with them. Right. But what I can say is be careful that you don't pick something that's really like expensive or tricky to obtain. Right. Because a lot of times throughout the use of them in the fuel cell, they get used up and they go away as they are, oxidized or whatever. And so you have to keep replenishing. You have to keep adding it, or you have to recoat your bioanode with more mediator as it goes away and things like that. So those are just some of the concerns, but I don't have more specific information for you than that. That does sound like something that's just sort of part and parcel to PhD research. You're going to have to try a lot of different ones and figure out which one, works best for you. All those kinds of things considered, I guess that's the best I can tell you. So,
all right. Very good. The next question is from Haotron. He says, "Hi, I have a question about EIS. What should be the embedded equivalent circuit if I have multi-layers, i.e. 3, on top of the base metal of stainless steel?
I have just the presentation for
How
you.
can I reason such a circuit?" Yeah.
I gave a webinar with such an example. Let me show you.
Mhm.
So you have a couple of options here. Okay, so there's one possibility. So this is an example. This is from a webinar I had given. You could just see the example here. This was someone had steel, and then they had hot dip galvanized steel of some kind on top of it. That's this like lighter gray layer, and then there was a biopolymer, and then there was electrolyte. So it was like a multi-layered, 3-layer, whatever, including the electrolyte, 4 layers. The simplest circuit would just be a bunch of RQs or RCs. So like this one here on the right, on the left, excuse me. That would be the simplest like answer to your question, is that at each interface you can put an RQ or a void element, and that captures the behavior. Now the tricky part is, are any of your layers porous in any way, shape, or form? Are any of your layers partially covering the underlying substrate, or are partially covered? Right? You could imagine, for instance, the one on the right here, where I have like my steel layer underneath and I have some coating, but both of the coatings are not totally covering the steel. And so electrolyte could also reach the bottom layer. So now I have this embedded model on the right, where I have the standard embedded model is something like this, where I have just 2 layers. But if I have 3 layers, you could imagine I have 3 RQs or RCs in parallel with 1. Alternatively, I could have it like this. If the first 2 layers are fully covering each other, right? And only the top layer is somewhat porous or impartially covered. And so I could have basically, like, I have my ohmic resistance. This probably could be up here in the solution, but hopefully you understand. There's an uncompensated ohmic resistance no matter what somewhere, right? But then I have an interface RQ here, and then I have like an embedded model on top of that. Okay. Now a couple of follow-ups with this are, number one, that these can all sometimes look similar. It depends on what your impedance data looks like, right? So to a certain extent, your impedance data like might have some kind of behavior looking like, I don't know, something like this, right? You could fit, for instance, that's a leading resistor, and right, this, applies to here. And then this part could be the embedded part, something like this. I'm drawing it shorthand or whatever here. So like here I have my embedded model applying to this piece here. And this could be a number of, like, this could be the 2-part embedded, or just the 1-part embedded, like I drew up here. So it could be this one, it could be this one. So this is a thing where a lot of times, and what I think I did in this specific webinar, it's on our YouTube channel. I'm not going to do the entire webinar again for you now, but I fit like multiples of these different ones as a hypothesis. Like, well, I don't know exactly which layer. It might be the porous one or where the embedded fit. So I'll fit this one, and then I'll fit this one and see which fits better. And that might be a way of answering your question of what the microstructure actually looks like. The other thing is that it is also entirely possible that this model simplifies. For instance, in an embedded model, what you often have is something that, instead of, I guess I'll just draw it in the simplest case. So this right here is like a full embedded model, right here. I'll zoom in. This is the full embedded model, right? But what we often end up having is that this capacitor and this resistor are neglected. Okay. And so what it ends up looking like is, I'll draw it sideways. I know it's sort of like up and down. It doesn't look quite right. You have this. This is what you might see in like papers, this kind of embedded model. So it looks like this is R1C1, and it kind of is. And then this is the other. So it's like two RQs, but one's embedded in the other. But you can see kind of where it derives from. It's actually that this goes with this and looks like it's one couple, but it's actually kind of not. This is the charge transfer resistance between the substrate and this film here, where this is the capacitance between the substrate and electrolyte because of the porous nature. So there's sometimes that is just what it boils down to. And so you can neglect some of these elements, and sometimes you can't. Sometimes it's better to keep them in. Sometimes what you do, for instance, is, and I showed this, I think, in the webinar, for instance, I did the circuit fit with like all of the elements there. I didn't neglect anything. And then when you got the value, this R4 here was like, 0.000001. And it's like, okay, well then it's basically neglectable. So that proves the point that it doesn't need to be there, and you can use the simplified version. But the most basic kind of approach is to assume there might be a RQ or a void element everywhere that there's an interface. And again, it's just drawing the interface and drawing the void elements on top of it. So wherever there's an interface, that's how I drew that. And so with multiple layers, yeah, it's an open question because you have more possibilities, right? Is it this? Is it this? Is it even more, here, like this? Is it this whole side? Is it just 3 RQs? Is everything fully covered? Does the electrolyte, make its way down to the bottom layer, to the second layer? There's a lot of open questions that you have to you might have to guess or try each fit and see how it works. But those are some, I don't know, talking through that situation with you. Try some of those embedded models and see how it fits your data.
All right, very good. The next question's from Sandeep. It's going through. Why we get a peak in CV, and why after the peak current, even though we increase the potential, why is the current decrease? So this is a good well-known kind of thought process that happens in a lot of electrochemistry. People should always kind of think about this, but the answer is ultimately due to mass transport. So when you have what you're talking about is you have a CV, voltage versus current, and then if you're sweeping, you get a peak, and then it goes down, and then you have something like this. You started here and you went this way, and it's kind of like, well, why does this not just like continue to go up, right? This is what we would expect from, say, Butler-Volmer kinetics. As I apply a higher voltage or a more negative voltage, I should get more current, but that's not what I get. We get this shape instead. And this literally has to do with diffusion. We're looking at the case where at the electrode surface, we have molecules kind of coming in and getting oxidized or reduced. But then at a certain point, we end up we kind of saturate the electrode with molecules that have already been oxidized or reduced. We need new molecules that are farther out from the electrode surface to diffuse towards the electrode so that we can get an electron transfer. But there's a low concentration of these guys like in this region. So actually an easy way of kind of showcasing this, give me 1 second, is to show you some of our simulation software. So I'm going to stop sharing, and then let me share one thing. I'll share my browser. Okay. Hold on 1 second. All right. All right. So this is our simulation software. So I think we should be able to see it.
Yep.
So we can simulate basic electron transfers. So if I simulate just a basic electron transfer, a reduction reaction, and then I have just a basic CV, and I simulate it, this is what we get, right? And what you're talking about, what's confusing is the fact that when we went from 1 to -1, and we did this reduction first, why did this not just keep going? And the reason why is, if you want to, you can look at the concentration profile as a function of distance. As the voltammegram goes, the red curve here is the species that's going to get reduced. We have full concentration, but as the reduction occurs, we now have this kind of diffusion layer. The concentration goes to 0 at the electrode, and it takes time for molecules that are further away from the electrode surface to go out there. You can see we have such a small amount of it that's close to the electrode that the current decreases. It's only when we sweep back that we get this kind of inversion, but then we still have the same problem. We have very little of this guy now that's getting oxidized on the way back. So the issue of why we get this kind of duck shape in the voltammegram, and it doesn't continue to give us more current, is because of mass transport. It has to do with the diffusion of molecules towards the electrode surface. All right, so hopefully that made some sense. Let us know if you have any further questions about that.
Meow has a question. It says, can you discuss a bit the difference between Butler-Volmer kinetics versus Marcus-Hush-Chidsey kinetics? So I don't have a ton of experience with the Marcus-Hush-Chidsey kinetics, but it appears from Marcus theory, which is a theory of electron transfer with like outer shell electrons and things of that nature. As best I can tell, for the most part, the main differences are that Marcus-Hush-Chidsey and just Marcus theory kinetics in general are more microscopic, and Butler-Volmer is more macroscopic. Which is to say that practically Butler-Volmer is used more often and is more descriptive of like what I would say real electrochemistry observed data is. It's more macroscopic, right? It's electron transfer, but it's what's microamps, milliamp, amount of measurable current from an instrument, and how the Butler-Volmer's kinetics, right? The exponential increase in current as a result of potential, whereas the Marcus theory or the Marcus-Hush-Chidsey kinetics model is born out of a more microscopic theoretical approach to the atom theory. What's the right wording here?
Atomic theory.
Atomic theory, something like that. Yeah. Just about electrons leaving. And so, for example, I found one publication from like 13 years ago that talks about how trying to review the Marcus-Hush-Chidsey theory, and how it should be more powerful and theoretically more powerful to describe kinetic processes than Butler-Volmer. And I think the reasoning being that it's more based in the atomic theory and like orbitals and electrons and what makes an electron move and how fast and whatever. But the end of the abstract is funny because it's touting this theory, but then it says results obtained show that it doesn't give a satisfactory fit compared to Butler-Volmer. Like Butler-Volmer is still the reason. So, as is sort of the case, I always like to joke about as an engineer, I'm more divorced from a lot of times the like bare bones theory of chemistry, where you're a chemist, you're more in touch with like the actual theory. For me, I'm like, yeah, I don't really care what the theory is. What happens? So it's like you can it's like, well, we take the theory and it should be this, but then when we multiply by 0.2, it works. So we just do that. It's like it doesn't, not to say that there's no theory behind Butler-Volmer, there is.
Yeah.
It's just generally speaking, that's kind of what I believe to be the case, is that it's the Marcus theory is a more microscopic, I don't know, first principles, atomic orbital kind of a explanation related to Gibbs free energy and things like that of the electron transfer. Whereas the Butler-Volmer's more of a, I don't know, practical and at least more observationally true. Just like the graph that Alex just showed with the CV, that increase in the current before mass transport causes a peak. That increase is pretty well described by the Butler-Volmer equation, and it's captured pretty well, actually. The beginning part of like a CV, for the most part, follows Butler-Volmer kinetics. It's an exponential increase in the current, and it does track with that theory. So that's what I can say about those two, I guess. So, and then, all right, let's move on here. So Zaki, I think, is next.
Yes.
Okay.
So Zaki is asking, what is the current to be multiplied with the solution resistance to find uncompensated IR? Intuitively, this should be the reference electrode current, as RE approximates the potential difference. So there's a lot of words that you described there, all kind of related, but there's a little kind of mismatch, just a little bit. So I think there's no reference electrode current, sort of say. There's only a tiny amount of current that passes through the reference electrode to make a measurement, but we're talking like femtoamps of current, a very, very small amount. And then when you're talking about the current that's to be multiplied with the solution resistance, I think what you're trying to say is, okay, there's you maybe you did some CV and you have some IR compensation, or you have some solution resistance, which is deforming your CV, and you're trying to correct for that. So there is only one current in your electrochemistry experiment. There's only one current, right? So there's just the current of the system. So current that's happening, that you're measuring at the working electrode, is the only current in your system. That current is equal and opposite to what's happening on, say, the counter electrode per se. So there's only one current that you can measure that you're multiplying by R to get the IR drop. So there's only one. So just keep that in mind. And then intuitively it should be and then you're taking that IR drop and then you're subtracting it from the potential that you're measuring between the working and the reference electrode. So that is fundamentally what we're doing when we're kind of compensating. And when you have a potentiostat that does IR compensation, you tell the potentiostat what's the resistance. It measures the current, multiplies it by that resistance, and then adds it to the applied potential so that you can accurately, compensate for that IR drop. So Zaki, I think that's what you're asking, and I think that's kind of the answer to the question. But can you, if you want to clarify exactly more about what you mean, I'm happy. We're happy to do that. But that I think should hopefully answer your question. And if you're thinking about like what is the current, I know we sometimes talk about like Faradaic and non-Faradaic current. Well, just the total current of what the instrument is measuring. That is the current that you would use in a in figuring out what the uncompensated, the IR drop is, the I to use in IR drop for your measurement, or for making the correction. Pardon me. Okay. So we have a series of questions from Shyla. and I think we'll go through this.
Yeah.
So Shyla is asking, sir, I'm working on copper oxide, which is a semiconductor used for photocatalysis or as a photocatalyst. I perform a test to prove that it's semiconductor using LSV, scan rate of 50 millivolts per second at a potential from -1 to -1.2.
I assume it's positive 1.2 because the next thing is they're saying they get a peak at 0.5. So I'm guessing they mean 1.
Oh, maybe it's
one of those
1.
numbers is probably not quite.
Okay,
That's
all right.
fine. Yeah.
It creates a peak at 0.5 using light, meaning it is a semiconductor. I was wondering what phenomenon was happening from going up to a 0.2 volt onset, then going down after reaching its max peak. Because not like HER or OER tests use LSV on specific potential windows. They just go up and down, indicating hydrogen or oxygen generation without having to be a peak like the semiconductor test.
It's the same. This is the same.
Oh,
question.
it's the same.
I think just
same question, just repeated.
Reworded. Yeah.
Okay.
So
wait. So let me see if I understand the.
I think what's confusing me is, so first of all, if you look at the standard electrode, the part of this that I don't know necessarily how to answer perfectly well, admittedly, is I'm not familiar with this test that you are saying is like a proof of a photocatalysis. I don't know exactly what you're referring to. This might be something I'm not aware of. Like you do LSV. I mean, I suppose it makes sense. Like if you do an LSV with your material, in darkness, and then you do one in light, and if you see a difference, I mean, I don't know that means it's a semiconductor. That might mean it's photoactive somehow. But anyway, there's some logic to what you're saying. I don't have a lot of personal experience with like that exact kind of experiment, I guess you'd say. But what I can tell you is that just look at for instance, this is the standard, like just the standard electrode potentials. So I mean, it depends on the pH and all that stuff. But like copper Cu2O is copper 1+, right? Copper whatever. So this reaction, I'm just looking at a standard potential, like you said. Again, I'm drawing some conclusions here because I don't know what pH you're at, what your reference electrode is, but versus NHE at like neutral pH. Minus 0.36, this is at least close depending on the pH shift and reference electrode shift. This is a possible reaction in alkaline, I believe, where you can, so this could be something that's happening. For example, that's a peak, is you're reducing the copper oxide to copper metal. That's a possibility. If I go down the table a little more, you can see, for instance, copper 1+ could oxidize to copper 2+ at just greater than 0.159, which is 0.2. So that's sort of similar to your potential. Possibly this is a reduction reaction, so which means if I'm higher than this potential, in theory, I'll push it the other way, which means I might be forming copper 2+. It's copper 2+ is the most stable form of copper, I believe. For the most part. So. One possibility I would say, if I'm just guessing, which has nothing to do, the potential window was -1 to 1.2. Yeah, that's what I figured, Shiloh. That was my assumption based on your peak being at 0.5. Obviously, that you went to that potential. So, but my assumption might have nothing to do on initially with the photo aspect of it at all. Is just that if you're getting a peak, it might just be oxidation of copper, excuse me, to a higher oxidation state. I don't know. Like maybe that's what it is. Maybe that's not. Maybe you don't see that in darkness, and so it is something has to do with it. I guess I don't know if I have any more information about that. I mean, I guess you're talking about why. One of the reasons why. Just I guess to your last point, I guess it's like, oh, you're talking about hydrogen evolution and oxygen evolution. The current just goes, or it doesn't always make a peak. The current just drops off one way or the other. And a lot of times it's actually just because hydrogen evolution and oxygen evolution reactions are usually at the extreme ends of the stability window in water. Once you start evolving hydrogen, you're going to just keep evolving hydrogen, forever. A peak, like,
there's a lot of water.
Yeah.
You have a lot of water
Yeah.
right next to your electrode.
I'm trying to describe it properly, I guess. Yeah, it's like you start reaching the limit of the electrolyte stability itself. Like a peak happens when it's like you have everything's stable in the electrolyte. There's a diffusion layer growing over time, but the electrolyte itself isn't just ripping apart. And OER and HER are like definitionally where the electrolyte is ripping apart. So I don't think it behaves quite the same way. Like you don't have maybe the same phenomenon of a diffusion layer growing in a regular way. Something like that is sort of why you see OER and HER a little bit of a different situation. There's gas being formed at the surface. It's like that breaks up all kinds of stuff, I guess. That can it's a different phenomenon. So I guess I don't totally know the answer.
Well, I think you like kind of said, like, you said there's a peak at, like, he says there's a peak at 0.5.
Right, but it looks like it started at 0.2 or something, I guess. I don't know.
Yeah. All right, so it goes up. So maybe it's a big peak.
It's a big peak, yeah.
But I'm like, I think you're right. Like, I'm not convinced based on the description that you're doing electrolysis per se. Right. Like you could just be like oxidizing, reducing, like you could just be reducing something, for example. I mean, it depends on, if you have a reduction peak or an oxidation peak. I assume it's an
oxidation peak. I'm just guessing. I could be wrong.
So he's going, because he was going from -1.
-1 to plus 1.2. So I assume it's an oxidation peak.
So he's doing oxidation.
That's why it seems to line up I mean, it lines up depending on pH and reference potential. It lines up a little bit with the copper 1+ to copper 2+. Which I just showed. So that's why I thought that might be what it is. I don't know.
Yeah. It's like, I'm not convinced that it is HER, OER, or an oxidation reaction that you would normally get with HER and OER. I think you are just getting a peak associated with a reaction specifically with copper. It's surface bound and mass transport limited, so you just get a peak. So that's my thought.
Yeah.
Is your copper oxide catalyst so good that it's moved the water or oxygen or the water electrolysis potential by like 500 millivolts? I'm like,
that's
I don't know about that.
I doubt it. Yeah.
So that's that's what I think. We're just guessing based on what you described.
Yeah.
So, but do a bunch of more tests. Like, see if this is reproducible. See what happens with and without light. All those types of things. But yeah, that's our 2 cents.
Yeah.
Okay. All right, moving on.
Nicholas is next.
Yeah.
So Nicholas says, "Hi guys, I'm working with SLG devices." What's SLG? Maybe
I did a quick search. It's just the name of a company. He might just be doing.
Oh, okay.
Interesting. But I don't know. But then again, I could be wrong. It could be something, an acronym for something. I don't know what.
Well, I don't think I need to know necessarily to answer your question because I think But I'm observing a quasi-semicircle at high frequencies around 40 kilohertz. I'm confident that it's a contact resistance. It sounds correct to me as well. How could I assure it's that and not know the problem? The simple answer, two ways. One, change the potential all over the place. Does it remain? Number two, change the electrolyte and change the system. Does it still stay? Because if you change those variables and you see the same or roughly the same semicircle, then obviously it is intrinsic to the material, the contact, right? The potential at which you apply your impedance set point should not impact the physical stuff. If there's a contact or a layer, sometimes we have a film and a substrate. It's like a very tightly adhered kind of a thing. You have a multi-layer, not like the embedded model that I talked about.
Single layer graphene. That's what he said.
Single layer graphene.
Ah, okay. Thank you.
Perfect. All right.
Okay. All right.
And in any case, same concept, right? There's a contact problem that should be unimpacted within a certain degree. If you go to like some crazy potential, you'll like rip apart graphene. Hopefully you kind of understand that. But I actually had the same kind of situation happened when I was in graduate school, making some films on materials, and I would always see this it wasn't even quasi, actually mine was almost a lot of the time I would have like a very small semicircle at the high frequencies, and I was convinced it was not an artifact, it was not a potentiostat problem, it was actually just the contact interface between like substrate and film, because it was very tight, there was no porosity, but that manifested itself. It's like it can sometimes, if you just have a measurable enough time constant, basically it makes a little semicircle, whether it's a quasi-semicircle or it's a semicircle, a fully formed semicircle. Change the potential, does it change? I found, for example, in mine, I changed the potential all over the place studying, whatever oxidation reaction I was studying, and that semicircle never changed within some measurement error. And it's like, well, clearly it's not a Faradaic process, externally or within the electrolyte. It's clearly intrinsic to the contact, as you say, or something like that. So try that, and then use the same material in a slightly different electrolyte with a different or no Faradaic process. Do you still see something resembling that? Then it's got to be the contact. It's got to be something physical. So those are the two ways that I would suggest.
All right, we have a series of questions from Chaying Chang. Let's see. I have a question about controller amplifier overload. I tried to measure the resistance of PiperION 60 micron AEM
anion-exchange
membrane in bicarbonate form at 60 degrees.
Okay.
Before the CV and potentiostatic EIS, I set a chronoamp of the working electrode to 2 volts. However, the measurement was stopped after a few seconds, and the system showed me the overload message. My colleague said
the current, I think.
Oh, the current was way too high. I checked, I ran the measurement at 25 degrees, and the value is half of the measured at 60 degrees. I don't know what the degrees are in this.
I assume Celsius.
Oh, this is temperature degrees. Okay.
Yeah, right. I assume this is the temperature.
Okay, temperature. Yeah. Value in half, that would be at 60. Would the too high current be caused by a high operating temperature?
Oh, absolutely.
Also, could you recommend any sources explain how to select equivalent circuit for different membranes? Thank you. Sorry, continue. What was your?
Yeah, no, sorry.
Yeah, the first part of the question.
Yeah, well, I mean, this is anion exchange membrane, but it's a similar phenomenon with proton exchange membrane fuel cells or anything else. There's a reason why they're usually operated at about 80 C. The performance is better. So, I mean, I have no clue whether to verify 25 to 60 is double. I mean, that sounds fine. That sounds reasonable, to be honest with me. I don't know what rate at which the current goes up, for example, but absolutely at higher temperatures, you're going to get better performance, which means more current. So yeah, I don't think that's unreasonable at all. Yeah, you probably, if you need to do some conditioning at 60, you might have to back it off a little bit if you're overloading your potentiostat, for sure. I think that's most probably what you're finding. And I don't have any, I don't know any specific, my ability to find one would probably be the same as yours going to, I assume you're in university, or at least somewhere with access to literature. We have somewhat limited access to literature. So other than me searching through the scientific database, for membrane electrochemistry or impedance, I don't know any specific sources or references off the top very quickly that I know, but I do know, I would say very, very broadly speaking, that in a lot of cases with a membrane, you get circuit elements that include things like finite Warburg elements, like Warburg short. And a lot of times it's sort of fairly obvious that you have a diffusion through the membrane, whether it's water, or in your case of an AEM, you have carbonate, bicarbonate, or hydroxide moving through a membrane. And so you have a diffusion of ions, anions in your case, going towards an anode or a cathode to oxidize or reduce. But it's moving through a membrane of set thickness, right? Your membrane is like 100 microns thick or whatever it is. And so diffusion through a set boundary thickness is definitionally a finite Warburg. So I think it's possible you're going to have a, I'll just sort of draw what I mean, I guess. And I don't know, again, it's not a specific reference, it's just my own experience or intuition. But you might have something like a resistor and then a, like a Warburg element with a CPE and something like a Warburg short. So this might be something that would fit with a membrane. Your Nyquist plot might look something like that, where there's like a little bit of a 45-degree kind of element to it in the beginning, and then it kind of curls down. It almost looks like two semicircles, but something like that can be the case. This Warburg short shows up sometimes because, again, you have that fixed length of diffusion. But you'll have to find some papers and sources. I suppose yourself, I don't have the best, set of references for that at my, ready to share with you, unfortunately. So.
Okay. The next question is from Anjali. He's asking, can you summarize electrochemical impedance spectroscopy?
Boy, can I.
But I would just say that due to the time, and we still have quite a few questions and comments going on, I might recommend there is we actually have a YouTube video. We have several YouTube videos on the subject. I'm going to put one. This is just the general YouTube video on impedance spectroscopy. That's like a pretty good, concise summary. But I would also recommend, I'm putting another link to our list of webinars, because Neil has, if you don't just want a summary, you want a full explanation of EIS, Neil has a huge list of webinars that you can access through our website. It actually takes you right back to YouTube, but it'll point you in the right direction, like where you can find a full explanation of electrochemical impedance spectroscopy. So I think we should do that for now, and then just for time's sake.
Yeah, that's a good idea.
Okay. And of course, Anjali, if you watch those videos and you still have questions, then come back to us. So Meow is saying, what would be your approach to try and measure a very small Faradaic current that is likely masked hidden by charging current? My initial approach was to conduct a staircase sweep or use an ultra micro electrode. I don't think that's a terrible idea. And actually, Nicholas actually gave a very good, it was actually going to be my recommendation, was to use differential pulse voltammetry, DPV. Is probably one of the best techniques for finding Faradaic currents under conditions where there's a lot of background current. And even if you use square wave or staircase is fine, square wave is fine, but differential pulse is really very good at detecting very, very small Faradaic currents that are hidden or masked by background charging currents. So I'd recommend using that. I just think we should go on to some of these other questions.
I want to just hit this one because Nicholas just asked us follow-up on EIS. So another EIS question, and it's mainly for you, Alex. You're going to love this answer.
Boy.
I'm doing impedance at minus 1.8 volts versus platinum, non-aqueous medium, and at low frequency. After the semicircle and low frequency, the y-axis basically goes straight down. What can that be? Can it be O2 reduction contamination? First of all, you're at minus 1.8 volts versus platinum. So obviously you have this pseudo reference electrode. Platinum as a pseudo reference electrode is like a really, really crappy choice. It's an unfortunate. I'm sure there's a good reason why you're using it in non-aqueous. You're sort of stuck with some pseudo reference one way or another. Platinum is like that's a really dicey one to use as a reference. It can kind of swim all over the place. So the first answer is that it might be garbage. It might be absolutely nothing. So run Kramer's Kronig. So for a couple of reasons. One of them is it's low frequency. So very possibly if things are drifting, if there's mass transport stuff going on, if the potential is drifting real bad because the platinum as a reference is a pseudo reference and isn't really fixed anywhere. Your impedance data, especially at low frequencies that are taking longer, could be all out of whack. And so the fact that it's going straight down means nothing. It could be going straight up, straight left, straight right. It could be nothing. Do Kramers-Kronig and see if the results are matching at those frequencies with your Kramers-Kronig results. Because I would have heavy doubts that, especially as the frequency drops farther and farther, that you have valid impedance any longer. There's probably a lot of drift happening, and it's probably getting away from validity. However, if it is valid, that tends to indicate some kind of inductive process. As the imaginary impedance axis goes down, becomes more negative, that indicates some sort of inductive process. Now, why? What is that inductor? What is it exactly? Why is there some sort of, strange thing like this happening? Those are all great questions. Nobody is really quite sure. It could be a contamination. There's theories for what people have used to describe these kinds of things. That it doesn't always go straight down. Sometimes it curls back towards the origin as well. Call it an inductive loop. It's Alex's favorite thing in the whole world. But see, I'm just kind of poking the knife in here. I had to get annoyed by the impedance potential.
Oh, the OCP.
Yes. So you had to get electrochemical potential and inductive loops today, just to keep you on your toes. So there's some reasons for that. Some of them could be water uptake. It's probably not for you. You're a non-aqueous. Radicals or intermediates or contamination, certainly possible. I guess O2 reduction is strange. You're at a really negative potential. Oxygen reduction happens at like one. You're like almost 2 full volts, like less than the oxygen reduction potential. Although I guess who knows?
He's a non-aqueous.
You're non-aqueous, so maybe
anything.
Yeah, it could be anything. Maybe that's not appropriate. Maybe you are right on because the non-aqueous is all over the place. But nevertheless, it's certainly possible. But I think my main point to say is that with this non-aqueous at slow frequencies, very possibly it's not valid. I would do Kramers-Kronig and double check that. You're going to have a very difficult time obtaining valid impedance data or electrochemistry data in general with a platinum pseudo-reference for sure, and especially at slow speeds.
Yeah.
So that's what I would say about that. I'll try to finish up here, I think, right?
Yeah.
Tonga has a question.
One question.
Sort of already answered this in the how to choose different techniques like DPV square wave against different concentrations of analytes. I'm just gonna, if you're listening right now as I'm saying these words, Tonga, you can back up the video on YouTube. We've talked about this a number of times. Within a few days or so, this video has timestamps in it. So if you're listening to this later, and the words you're hearing are later, then right this exact live moment, it's like trippy to speak like that, but this is a video on our YouTube channel that lives, and there are timestamps. And so we have covered this in the previous 2-ish hours. A couple times talking about, Alex gave a good overview of CV, LSV, DPV, square wave. And we just discussed, as you said, Meow asked a question about what should I do to check on Faraday current, and Nicholas gave good advice of DPV. So we just discussed some of those things. So we're going to kind of move on. I just wanted to mention that these have been answered in this live stream. So check the timestamps and back up the video by a little ways, and you'll be able to hear some discussion of those techniques. And then I think we'll answer Frederick's question. That's the last one.
Yeah, I think that's the last one. Yeah, it's a very good question.
Yes,
I'm actually happy he brought this question up.
Yeah. So Frederick says, is IR compensation always necessary? Most catalysis studies do IR, but there is also 0.9 or 0.95 or even 0.5 corrections. Is IR misused to over-report performance or misunderstood? I don't think it's misunderstood. I do think that perhaps you're not. We can discuss this very briefly. The simplest explanation for you, and perhaps maybe this is your misunderstanding, if there is one. Why are people using 0.9, 0.95, or whatever? The reason is that when you are running a potentiostat and performing IR compensation actively, if you compensate for 100%, you will cause the potentiostat to oscillate uncontrollably and your data will be garbage. So practically, you cannot really compensate more than about 90%. Sometimes it's 80%. It depends on the situation, the potentiostat, et cetera. But there's the reason why those are compensated for at 90% or 80% or whatever is a practical one, more so than some sort of misunderstanding, I would say. It's a potentiostat thing, right? And then practically, the amount of error in your current or voltage measurements or potential measurements between compensating 100% of your IR drop versus 90% is negligible in most cases. So it's more of a practical thing. I don't know if you want to say more about that. I just kind of set that up there.
I actually think it is misunderstood. I think a lot of researchers do not understand IR compensation. I think a lot of them.
Well, that's probably true.
I think that they don't fully, because a lot of people who are doing catalysis, they're interested in synthesizing whatever their molecule is. They made this really cool whatever. They barely know enough like electrochemistry and cyclovoltammetry, and there's really very little. Sometimes there's very little like rhyme or reason why they pick 0.9 versus 9 versus 0.95. We're also talking about like a percent contribution, which is to say they determine what the solution resistance is, and then they take that value and then they multiply it by 0.95% or something like that, and then use that value. And then you even mentioned there's even a 0.5 correction. 0.5, like, why are you compensating for half of the solution resistance? Right. So I think a lot of people just use a wide variety of different numbers without really knowing what the resistance is. And certainly there are a lot of instances where like, are they doing IR compensation in the bulk electrolysis for a catalysis study? Because if you are, you probably don't need to. Like, why would you have an active IR compensation for bulk electrolysis? It makes more sense in the cyclic voltammetry experiment. You could just apply a higher voltage, and get the same result when you're just applying a constant voltage to your system. So IR, and the question of, is IR compensation always necessary? It depends. It depends a lot on the system. And yeah, I think you also do run into the issue where you could over-report performance because of IR compensation. That's definitely possible because you're applying more potential when you do have IR compensation on. And ideally, it should be more accurate because you are overcoming the resistance in the solution. But yeah, some people just pick arbitrary values sometimes about whether it's 0.9 or 0.95 or 8 or 0.7 or something like that. And they just do it sometimes because it was in the other literature article or something like that. So there's a part of me that feels like it's somewhat misunderstood. Like some people don't really understand IR drop.
I'm sure that's the case.
That may also be another thing.
I think broadly speaking, you're right. There's definitely misunderstanding about it. It's a little bit of a tricky concept.
Yeah.
Particularly with how the potentiostat works. And Frederick followed up saying, I did misunderstand a little. And I think that's my main part of the feedback was about just the 80%, 90%, where that comes from. That everything you said is true. People could over-report, could overcorrect, and that's when you're saying the slope inverts or whatever.
Yeah, I mean,
like that's where that's
slope inverts.
that would be like okay, so if you overcompensate, for instance, it's like adding, it's like you're reporting. Okay, so the bad part about, for instance, when you have IR drop and you get like some really cruddy looking CV like this, right? What the reality is that at this potential, it's like if you were to do this without IR drop, you would get like, whatever. My drawing is terrible, but the reality is at this potential, I should have like this current but I only have this current, because the reality is I'm actually at this potential. Like, in other words, I'm overestimating the potential that's actually occurring at my electrode. It's like, this is the potential here. So I should be at, like 0.6, but I'm actually at 0.4. So, oh, that stinks. But overcompensating would be going the other direction. It's like, oh, well, I think I'm at 0.6, but I'm actually at 0.7. So I'm over-reporting a current inappropriately. Like, IR drop usually goes the other direction. It ruins your, oh, why do I only have 10 milliamps or 10 microamps at 0.6? Because I'm only at 0.4. That's why. I'm not actually at 0.6. I'm losing all of this stuff because of IR drop. Well, if on the other hand, you're saying, hey, look, at 0.6, I should be getting 10 microamps, but I actually have 20. My catalyst is amazing. It's like, no. You're cheating. You're actually at 0.7 because you're overcompensating. And so that inversion will happen. If you overcompensate, you'll get like, you can have some weird, like, something like this.
Yeah, get some.
It starts to look like
a
deformed. Yeah.
And actually,
so
and
it's
this,
like it goes backwards.
This is another problem. You can get a perfectly good looking voltammogram, but if you don't check the peak splitting, it could be like, 55 millivolt peak splitting.
Yeah.
And that's technically overcompensated. It doesn't mean that the potentious, like, it looks like a perfect voltammogram, but it has the wrong values.
Yeah.
So that's why it's such a, and that has to do with other things like stability filter settings. Like, there's a whole lot of other stuff that's involved, and how fast is the potentiostat, monitor things. Now, to answer your other question about, like, do you have a useful source to explain in more depth why 90% is safe? Well, I actually don't even know if 90% is, quote, safe, because if you have 1,000 ohms of solution resistance, then you're only applying 900 ohms of compensation. But if you had 100 ohms, then you would just be applying 90. And there's a big practical difference between, like, applying 90 ohms of compensation versus 900.
Yeah.
Because each ohm is more important, if you're measuring milliamps of current versus microamps of current.
Yeah. And to your point earlier, there was someone asked, again, check the timestamp. Someone asked, what's the current associated with the IR drop? It's the current that you measure.
It's the current that
right?
you measure.
So if you're measuring, just the most extreme example, 1 amp, it's crazy, right? But it's like, and then you have 10 ohms and you compensate 90%. You still have 1 ohm times 1 amp is a volt.
Yeah.
Okay. That's an extreme example. Let's take it down by an order of magnitude. 1 milli, let's say it's a milliamp, right?
Oh, yeah.
100 millivolts, whatever. Okay. So you have like 100 millivolts of difference. Multiply that by 10 and you have like 10 volts, a volt. Like, it quickly scales.
Yeah.
So 90% of 1,000 makes a huge big difference between 90% of 10 or 20.
Yeah.
So that absolutely makes a big difference. But to your point, as far as, but safe from the perspective of inverting the slope, you're only going to have that kind of inversion when you're more than 100%. So what that usually comes from is when you're not compensating by percent and you're compensating by a number, because you don't know what it is. You're doing like 10, 100, 200, 300 ohms, 400 ohms. You don't know what it is. If you've accurately measured the IR drop and you're able to type in a percentage, the safety, if you will, of not inverting your slope, just don't go to 100%.
Yeah.
If you go to 150%, it'll invert. Like this, you'll have a phenomenon where 90% it's okay. And then at 100 or 110 or whatever, it'll be like, it'll oscillate. And then you can go beyond that and it stops oscillating, but then it's inversion. You're overcompensating. That's the progression. So when you're doing percentages, it's obvious. Don't go to 100%, right? If you're doing numbers, that's when you can run into problems. If you're doing positive feedback, you can overcompensate and stuff like that.
Yeah.
So,
the peak splitting, the split in the peak position is another check. If you're working in a non-aqueous system and you have ferrocene, you can look at the ferrocene peak splitting, because that's supposed to be very fast.
That one's got to be very, very spot on. Yeah.
So that one would be spot on, where, real catalysts actually may have real peak splitting that's bigger than 59 or 60 millivolts.
Exactly.
Stuff like that. So that's another thing to look for checking overcompensation.
Okay.
He just says one line, isn't also dependent on the highest current measured.
No, it's only the current at that potential being measured.
Yes.
That's why IR compensation is necessary, because the IR drop is I times R. I is changing. In theory, R is constant, but I is changing as you sweep through. So as the I changes, the IR drop changes. It's actively changing.
Mhm.
And so the IR compensation experiment, when you have a high IR drop, is really good, because as it increases, it is adjusting on the fly for the magnitude of the IR drop as it is also increasing or decreasing.
Yeah.
So
Yeah, we can give a whole thing on
we have
IR drop. I mean,
you have a video
this is-
on it, and I did a webinar on it too. So
yeah, that's right. There are those two resources that
yeah,
explain that. But we don't explain enough in the context of catalysis, but
yeah,
we do explain what it is and stuff like that. So it's on the YouTube channel, and Neil has a webinar. It's Neil's webinar on how potentiostats work.
Yeah.
Where he goes over.
I think it's called How Potentiostats Work and IR
Compensation,
something like that.
Something
Yeah,
like that.
It's on our webinars
playlist,
so go check that out. Yeah. Okay, we're gonna call it there.
I think that was good.
It's been these are great questions. Thank you all very much. We I suppose we're good next week. Maybe slightly different timing, or maybe not. We're not sure yet. Anyway, check our YouTube and LinkedIn pages for the timing of next week's live stream. As always, we appreciate everybody's engagement and questions. And take care, everybody. Have a good one.
Bye.